met yesterday. My name's Philip Cardiff. If you haven't met me before, I'm sure some of you have had me from Manufacturing Dublin. So I'm the module coordinator for this CCM2. So what is this module about? So this is obviously related to CCM1, but CCM1 is theoretical computational continuum mechanics, whereas CCM2 is more like applied computational continuum mechanics. So they're both looking at the same content, but they're looking at it from two different perspectives. So this comes very much from looking at it from the software perspective and linking that to the theory. And there's more emphasis on things like numerical methods, whereas in CCM1, it's more on the mathematics and the physics. But they're both doing the same thing. So how would you solve any of these questions? So let's imagine you're working for a company like Vestas who make wind turbines, and you get a contract to make a wind farm somewhere like in the west of Ireland, and you're trying to figure out where exactly to put the wind turbines and relative to each other where they should be relative to the prevailing winds, for example. And so clearly you can see like there's lots of, there's wakes behind each of them that will affect the efficiency if you have a farm. Companies like Vestas, they will use softwares like OpenFOAM or Fluent. So actually OpenFOAM seems to be the one they use. And they'll have some sort of internal software that you can place like little dots where you want to put the wind turbines, and then press go, and then it'll set up automatically and run an OpenFOAM simulation on a cloud, and then come back with a report. And things that they're looking for is, well, one is efficiency, but more critically is to do with the fatigue on the blades. So if you imagine you have a little hill and you put a wind turbine just after the hill, then you might get a big recirculation zone. So that means when the blades are higher than the hill, they're blown one way, and then they come down and then they get blown back. So you start like accelerating the fatigue failure of the blades, for example. But there's lots of things you could look at. If you're into aerodynamics, then clearly cars are all simulated with CFD. Every car company now will do this. And so like the Tesla truck, after they released it, then within like a day, external people had done CFD on it. In Tesla, have obviously internally done that, but they didn't release it. So if you look at the coefficient of drag, which is a measure of how low the drag is, basically, it's particularly low. It's much lower than any other truck out there. So the shape, they actually designed it to try and reduce the drag. Similarly, in Formula One, so Formula One teams have a limit on the amount of computation they can do per year. So that's regulated. So they can only use, I don't know what it is, say 1 million CPU hours. So they can only run a certain number of simulations, because if they just let them go free range, just the bigger companies just will optimize too much the aerodynamics of their car. And that's why every year they change things, and the regulators force them to put little bits on the car, like behind the wheels and stuff like that, that mess with the aerodynamics just to try and make it a fair playing field. So when they make any change to the car, they have to show the models that they ran and how expensive the models were, and show that it's within their quota. I don't know how well that can be policed, to be honest. I mean, who says you can't have a computer at home running all things, but okay, these are big models. Sorry, I'll move my face. Right. Actually, I'll put this one here. Oh. No. So how do you design a wing or a fuselage so that it will not break or deflect excessively? So many stress and structural mechanics applications, there's, let's say, static loading. You just, whatever static loads it's under, you don't want it to break. It's fair enough. But an awful lot of times, fatigue is the issue. So you look at the maximum load and the minimum load, and you look at that change in stress, and then you will try, from Paris's law, predict when the material will fail or how many cycles it will take to fail. So all these aerospace companies will be doing that for designing any of their components like that. So these are wings, and you can do things like modal analysis to check things on buckle as well. Or how can you be sure a stent will not fracture during deployment or fail prematurely? So medical device companies, like many of you will have been on placement, maybe like in Stryker, Dupuy, Medtronic, Boston Scientific, companies like that in Ireland. They will often use stress analysis tools. I know Medtronic and Boston Scientific use Abacus. Both of them use Abacus for their stents designs like this. They will use Abacus to try and model. And once again, fatigue is often the thing that comes up, but also just a static analysis. So some of my own research interests. I do a lot of work and supervised PhDs around metal forming simulation. I work with a Belgian multinational called Bakeard. You may vaguely remember from manufacturing, I probably brought them up as case studies. But I work with them making models of their metal forming processes like rolling and drawing and helping them to optimize their processes. And for example, like an oil company might want to make pipes for coming from the seabed, and they're reinforced with giant steel rods that reinforce the pipes. But to make those dimensions and at huge quantities takes Bakeard years to design like 10 sets of rollers to actually meet the tolerances at their required processing speeds. So they use models, and I help them with some models to try to achieve that. So you can kind of do hypothetical simulations or hypothetical tests. So they might say, well, here's 4 or 5 designs you want to try. Each design will take them 6 weeks to 3 months to make and test. So if we could just do all of them first and say, well, some of them are terrible, the other ones we're not sure they might be good, and they might try those ones. Try those with that. It's clearly not just mechanical engineering. It's not limited to mechanical engineering. So like chemical engineering, mixing reactors. I'm not sure if anyone here is in chemical engineering. Sometimes chemical engineering PhD students take it. So I know there's lots of people in chemical engineering, and they use softwares like OpenFOAM and Fluent for like reactor design and mixing. So for example, if you're trying to mix 2 fluids to speed up the reaction, you want to have as much interface between the fluids as possible. So for a given energy input, you might want to maximize that. So you could 3D print a design, or you could have like a mechanical stir or something like that. In the civil engineering space, there's things like building comfort, or pedestrian comfort. So when large buildings are designed, and this is even the case in Dublin, that if you say have a nice little tree and a bench, the architects put in for someone to sit at, well, nobody's going to sit at it if the wind's over 2 meters per second on average. It'll be blown all over the place. So there's a scale called the Lawson scale that will tell you people are happy to walk in this wind speed, they're happy to sit in this, they're happy to drink coffee in this, they're happy to do both in this wind scale. So when the architects come up with designs, they send it off to companies. There's lots from around Dublin, companies like Arab and other mechanical services companies like that. And they can do safety analysis, and they will say, well, it's actually pretty windy in this spot. We suggest you stick more trees here, or a canopy going down above the entrance of the building to divert the wind. So this building is called a Flatiron Building in New York. And you always see like in frames and stuff that I show this building there. Some of you, like loads of those New York-based sitcoms, I have pictures of this. But it was built, I don't know, early 1900s, but it's apparently terrible for wind, pedestrian wind. People get blown over when they're walking around it. It just happens to be designed like a perfect like airfoil. So people at street level they obviously didn't do safety in the 1900s. So it just happens to be a really terrible job for pedestrian comfort. Staying in the civil engineering space, bridge design as well. There's lots of reasons you might be interested in that. Obviously, there's the structural side, shouldn't fall down. But then there's the wind side. You don't want it to resonate like the Common Arrows Bridge and collapse. And so you might look at the resonant frequencies in the wind. So vortices will be shed off the cables, and they will shed at certain frequencies, and you want to check they don't correspond to the resonance of the bridge itself. So I'm not saying all of these things I've shown. It's still the default way to solve most problems in engineering is not to go to complicated simulations. It's just figure out the easiest way to do it. But oftentimes the easiest way is actually just to simulate some cases. And another example is forensic engineering. So I've been involved in some cases where things break that aren't meant to break, and then one company sues another company. Or in worst case scenario, someone actually gets hurt. So I wasn't involved in this, but this was in 2004. The new terminal, part of the new terminal in Paris, if you ever been to Charles de Gaulle's pretty cool terminal, but part of the roof collapsed and it was just under design. So I'm sure they did FEA on it. It's just whoever did it didn't do a great design. And so I don't know what the outcome of that was, but I know I was involved in a separate case, like a small one in Ireland where something collapsed. I know they did stress analysis, but they basically did linear stress analysis and that ignores buckling. So if you have any thin part, if it didn't buckle, it wouldn't have failed. But thin parts fail due to buckling, not due to just overload of standard stress. So they're the kind of ways that people can mess up on things. Nobody was hurt in that case. Okay, a question I have for you. So why would an engineering company use numerical modeling instead of performing experiments? Anybody think? And open cost? Very good. Yeah, that's one. Cost. It might just be cheaper than an experiment. Often experiments are really expensive. Often because it's time. So time and cost are kind of the same thing in companies most of the time. If something takes long, it's expensive. Sometimes. Anything else? Go over here first. I didn't hear. Repeatability in what way? As in, if you do an experiment, it typically isn't as repeatable. As in, if you do it 3 times, you get 3 different answers. Is that what you're saying? Or maybe you want to change a small parameter. Oh yeah, sure. So once you have a model set up, you can just change some parameter, run it again. Whereas an experiment, you just have to do the full experiment again. Yeah, fair enough. You were saying similarly. Very good. Anything else? In terms of sure. So materials and resources and everything. Yeah. Probably companies most of the time just care about cost. Yeah. yeah. Us engineers are about that, but the managers are just like, well, what's the cheapest thing? So yeah, definitely. Anything else? Anything a model can give an experiment can't, or more accurate data? Yeah, sometimes people say this, but not really. So the example of will a wind turbine blade break after 1 million cycles? If you build one, you put it out for 10 years and it doesn't break after 10 years, then the answer is no. You make a model and it says the same thing. Well, you don't know for sure until you actually ran. So let's say you made the experiment and it did break and the model says it doesn't, which one's right? So, but yeah, that maybe to change it a different way, insight. So if you do a test, say like in the metal forming examples I gave, or actually any of the examples, like the wind pedestrian case. Sorry, I'm going to go back over here. There's certain things you just can't measure experimentally. So if you want to know what's inside that metal forming product, like you want to know the distribution of permanent plastic strain or permanent strains, and you want to know like the distribution of stress and strain or other things like where the rollers might break or something, that information, it's almost impossible to get that in an experiment situation. And so when you have a model, you can just look at the value of anything anywhere, and that's just not possible in an experiment. So there's, let's say, insight that you gain from models that isn't as easily or as readily available from other methods. So it might not give you an answer yes or no, but it might help along with experiments for you to solve whatever problem you're interested in. There's water dripping down from the outside, so I don't know what that is. I should probably tell somebody about that. So experiments are typically expensive. Simulations can often be cheaper if you have someone to do them, who is an expert in them. So you may have to pay for software, you may have to pay someone a little bit more to be an expert in simulation, and it will take time as well, but typically it's cheaper. And then they provide a unique insight into the physics, which isn't always possible. And more accurate is not true, typically. They're not more accurate. Okay, so that's all the background for what this module is about. That sets the scene, but maybe just get down to the actual details. Your questions are going to be like, what do you have to do to pass this module? So in this module, we're going to learn how to perform numerical simulations of solid and fluid systems. So there's loads of types of simulations. You can have like electrical simulations and all sorts of things like that. And like designing motherboards, you might look at the flow of electricity or something like that, and accompanied with heat or something. But we're not going into those types of physics. We're just going to look at solid stress analysis and fluid, like CFD style analysis. You can look on the module descriptor. This says gives like an overview of all the different components we're going to look at. And so basically linking continuum mechanics theory with practice. So the emphasis is very much on practice. And then we're going to use this Abacus, ANSYS, Fluent, and OpenFOAM softwares. And we're going to do some heat transfer, which we started, some solid mechanics, fluid dynamics. And then hopefully by the end of this module, you're going to know how to set up a model. What are the steps to set up a model? And what are the important things like boundary conditions and things like discretization error and stuff like that. And understanding errors is really critical. So we're going to spend a lot of time focusing on that and how to verify and validate results. And then we're going to end up with a little bit on the Unix and Linux environments, and because OpenFOAM typically runs in a Linux environment. And yeah, at the end, you'll be able to run your simulations for Abacus, ANSYS, or OpenFOAM on supercomputers. So UCD has a few supercomputers, and then there's one Irish one which is shared between universities. So you can get access to those and waste loads of electricity if you want. Oh, and the other thing to mention is I'll always ask for get feedback maybe halfway through the module and then at the end as well. That sometimes people wonder is 3 softwares is not too many. Should we not just focus on one and become an expert in that? But I don't think so. If we just focus on Abacus, then you go out and get a job in say Stryker, they use ANSYS typically. They're not going to change the Abacus just because a graduate engineer said, well, I learned Abacus and engineering, right? So it's better to, let's say, learn to perform simulations in a somewhat agnostic manner. So if you learn a few different simulations, and what I'm focusing on is you just know the steps. All of these softwares have the same steps: boundary conditions, meshing, geometry, materials, loading conditions. If you just know that any software for simulation has those steps, then you can learn any software relatively quickly. Okay, the buttons will look different in different places, but it's the same thing underneath it. So that's why we use 3. And then also OpenFOAM is an open source one as well, just to mix it up, because it's free. If you go to an SME, they may not be able to pay €50,000 per year for an Abacus license. So typically an Abacus and ANSYS license for one license commercially is about €50,000 per year. That's before they pay you to use it later, and presumably about the same. So you can see how it gets pretty expensive. So in universities, we get a 95% discount, so it's like €5,000 per year or something. But OpenFOAM is free, so that's why it's useful to introduce to open source softwares to you as well that may be useful. Okay, how do I pass the module? So there are 3 assessment components or summative assessment components. So the big one is called the individual project, or I think I call it the mini project online. So the mini project, at the end of it, it's just a report, a 3,000-word report that you have to submit. So I'll talk a little bit more about that as well, to do with deadlines and things like that. And in advance of it, you have the option to submit, I think it's a 2-page plan. So kind of you set out what you're going to do. I think that's at week 9. And then I will, within a week, come back and give you feedback on that. And that's not graded, that plan. You don't have to. But if you want to get a good mark, it's probably useful to get my feedback on what you're going to do before you do it. And then the idea is in the labs, and you can chat to me about your ideas in advance of that, and I can help you form what this mini project will be on. The other components, 10% for the weekly labs. So there are 9 weekly labs, and you've mostly done 1 already. So it wasn't that much involved, I think. Apart from that, a lot of the time was just waiting to install the software whenever you have it installed. So week 2 will be a little bit more involved, week 3 a little bit more involved. And then we go on to ANSYS. And we do the same for ANSYS, 3 weeks, and then OpenFOAM for 2 weeks. So there's 9 of these assignments. There's not too much apart from you just have to be able to follow a tutorial and then just take a screenshot and show you did it. So that's why it's only 10%. It's not like a big percentage. But assuming you do all of those things, you should all get that 10%. Then there's online quizzes. I haven't put them up yet. In the next week or 2, I'll do it. So there'll be 3 quizzes on Brightspace. So you can do them in your own time, and you can do them up to 10 times each. So I could make it unlimited, but then you're all engineers, so you'll just adopt the brute force approach where you're just not answering anything. So the reason I make it 10 is just so if reduces the likelihood you're going to do a brute force approach. Also, it's less likely because every time you do it, it shuffles the questions and the answers. So it gets a bit messy to do a brute force approach. So all of this is me trying to just get you to actually learn whatever the questions are. So these are things I would like you to have learned by the end of the module, and the way I'm trying to get that to happen is via these quizzes. And so the first quiz is broadly related to Abacus, and then the next one broadly related to ANSYS, and the last one related to OpenFOAM. So that's the extra 30%, probably based on previous years. If you're resilient and tenacious and stick at it, you can get most of those percentage points. Sometimes people are just happy enough with their 80%, which is fine as well. And then I guess the main thing that differentiates the final grades at the end is in terms of the mini project itself. The scale that I'm using is this alternative linear scale. So it's a linear scale, so it just goes in 5% increments. So at first this looks difficult because it's like, you have to get over 85% to get an A. But the way everything's graded is done with this in mind. So when I'm going to grade your reports, I'm not going to give a mark. I'm going to give, is this an A report, a B report, a C report? It doesn't matter what the corresponding percentage is. And then in terms of the tutorials and the labs, well, if you just get 100%, it doesn't matter. But it's very achievable to get 100% in both the tutorials and the labs. So in that way, it doesn't actually make any difference. In fact, it's actually more unfair when I previously used to use the nonlinear scale, because you would have someone who gets a B- and a B+, and they would get, what is it, like 71, or was it 61 versus 69? And then it goes to A- and it suddenly jumps to like 75%, and then A+ suddenly goes to 85% because there's like big 10% chunks for the A's. And so it was unfair for the way. You probably have more questions on that, which I can come back to. How's the module structured? This you already will have known, I guess, since you're here. So there is one lecture every week, and I put the slides up online, and then we have weekly labs. So they were split in two groups just to do with spacing in the room, and the number of computers. But since most people are using their laptops, it's fine to turn up at for everyone to turn up at 3 o'clock for the labs. So if you are scheduled for the 4:30 start, just feel free to come at 3. You can come at 4:30 if you want, but you can feel free to come at 3 o'clock. So the labs, there will typically be at least 2 teaching assistants and myself at the labs. And as you'll have seen, it's all online, so you can do them in your own time. But we can guarantee that we're available to answer your questions and help with if you turn up at the labs during the lab time. So if you leave them all to the year, at the end of the year, and then you send me an email saying, I need some help with things, or are you around? And then I can say, sure, I'll be there at the lab, but I would prioritize people working on this week's lab first. And then if there's extra time, I can help you. Yeah, you don't get grades for turning up to anything. So it's just whatever's the best for you to learn. Yeah, typically week 1 to 3, or the first 3 weeks are assignments, Abacus, then ANSYS, then OpenFOAM. So Abacus is heat transfer and solid mechanics. ANSYS Fluent, which is one package in the ANSYS suite, is a CFD, a computational fluid dynamics software. So it's a fluid flow software. OpenFOAM is an open source, mostly fluid flow software, but it does other things as well. And then the last 3 weeks, you'll be focusing on your mini projects. So the lab time, you can turn up and try finish some labs you're going to be behind on, that's fine. And we can help you with that. But if you turn up and you're trying to figure out what to run your projects on, or like to formulate whatever your project is, and you need some help with that, or you need some technical help, that's what the labs are for. Okay, so let me see. You probably have some questions on some of these things, I'm guessing. A lot of this information will be on Brightspace. So one thing actually I didn't realize, a few people noticed for the assessments, actually, let me change this to student view just to make it look more like what you see. So if you go to your assignments, there was no assignments appearing for some people like that. But I think I sent an announcement earlier today that you just have to fill out a student integrity declaration. So basically the idea here is, since you can do these on your own, and there's a certain, let's say, you have a certain responsibility to uphold academic integrity. So can I stop you just copying and pasting all of your housemates' answers? No, I can't, but I can ask you to read this and agree to this. I also can't stop you robbing the local centre, something like that. So, I mean, so why don't you do that? Why do you think one's okay and one's not okay? So that's maybe just read these things. So I am encouraging you to talk and discuss the questions with your classmates. So if you don't understand something, a lot of the ways I learned is just talking to a peer. So if I ask my friend to explain something to me, or if I explain something to him, that would often help me or him understand or her understand. And so I am encouraging that, but I'm discouraging you just saying, hey, Mary, what did you get for this one? And then they just come over your shoulder and just tell you to take it. Okay. So you have to click on that and accept it, and then you can submit things. So you'll have the weekly labs all here, so you can flick down to them. There's these tutorials. For the Abacus ones, I re-recorded them because I recorded them a few years ago. The ANSYS ones I haven't done it yet. You're going to do it next week or something like that. But if you want to jump ahead, they're still fine. The ANSYS tutorials and the OpenFOAM ones, but I'm in the process of re-recording. So there are all your weeks. If you wanted, it isn't a requirement to have done CCM1, and let's say the theoretical aspect, but the notes are there in case you don't have them or you want to look at them. It's basically very similar to Shaun's outline series on continuum mechanics, and with some extra numerical stuff at the end, in case you want to look it up. It's not necessarily required. There's other optional video tutorials. These are just other tutorials that we're not covering, that it's mostly for if your mini project happens to use some other features that we haven't covered in a tutorial, you might want to look them up, or if you're thesis projects. Anything else here? Yeah, the quizzes will appear here under assessment. And I think I made a discussion form. If you want to ask, you can ask anonymous questions. I've set it to be, you can be anonymous. So if you want to ask a question you don't want to ask in class and there's some problem, or you just want to complain about something, it's fine as well. Constructively complain is helpful. Otherwise, well, you don't have to, you just vent if you want to. So you can do that there. You can send me an email either. Yeah, that's everything. I guess for you, the project, maybe I can just tell you a little bit more about the project. So let me get out of here because it's not visible. I haven't made it visible yet. Assignments. I think I can actually make that visible now. So these would be all the assignments you'll see. So week 1 to 9, and then there's mini project ungraded, or mini project plan ungraded, and a mini project report. So the ungraded plan you don't have to submit, but I suggest you do submit it if you want to try to get a good grade, and then I'll get back to you with a week feedback. But if we go into the mini project, oh no, not view submissions. Edit assignments. Yeah, so this is it here. So I'll make this visible when I go back to my office after this. So I give a mini project overview, which explains what you have to do. And then the mini project report guidelines, essentially like a rubric or like a table of this is how I will grade. So, so the overview is just the 2 pages that explains what the goal, or it's 1 page, but just explains the goal of this project. So you're tasked with creating a model to analyze some topic related to your current BE, ME, PhD thesis project. Some of you may, if you're in 4th year, you wouldn't be doing your thesis project now, so you could base it on if you did the thesis project in 3rd year. And if none of those things apply, then just come to me if you have an interesting idea you'd like to run a model on based on something you saw previously or are interested in, then we can come up with something. So it should be based around some current project or previous project. Models should not examine the primary focus of your thesis. So you will be assigned, if you're in 5th year, you'll be assigned your master's thesis project next week. So you shouldn't just do something you're going to do. If you're doing a CFD model of arteries, then that should not be your mini project. That's your main thesis project. And we can't assess them twice, but maybe you'll do a stress analysis of the walls in the arteries. So that isn't something you were going to already do. It's something that's complementary. It's still useful, but it's separate. So we're not assessing something twice. So the model should perform at least one of the following functions. So it should facilitate understanding of the chosen problem, or aid in decision-making by simulating what-if scenarios, and or explain, control, or predict events or performance. So that's kind of the purpose of any model. But the reason I have to explicitly state that is often people just want to model things. And I see this with thesis projects as well. I want to make a model and there's no purpose to the model. It's just, I want to make a model of a 3D printer. I'm like, okay, what's the model going to do? Like, no, just model 3D printing. I'm like, well, is it for designing the 3D printer or the part or understanding the stresses? Or so it's very difficult to make modeling decisions, which are all approximations, if there isn't a goal to it. So that it has to be very clear. So you have to use one of the softwares, and then there's some other information here. And then that second document just says, this is what the report must look like, how many words it should have, what sections it should have, what content it should have, and this is the rubric I'll use. So when I'm grading it, this is what I look at. So you can see the choice line it up. I think I give a description for the plan. If you click into the plan, it says what I expect for the plan. So it doesn't need all that information. I just need to know what, I think it's just, what are you going to model? Give me some background so I understand the problem. And what is the purpose of the model? And then what software you're going to use, and like what's the mathematical model you're going to use. So we're going to talk about that, but things like what boundary conditions, what geometry, what materials, what loading conditions. Okay, so I will share that when I go back. And actually, is it visible? Maybe it is already visible. Actually, it is. Okay, yeah. It's just it doesn't. I hadn't, obviously as a student, hadn't done the student integrity declaration. Okay, so they're there, so you can check those out and see them. Yeah, so you can come up with your idea, and then each of our labs, just you can chat to me or any of the TAs, and I can help, or we can help direct you to what's a reasonable thing. I would say the opposite of what I'd say in life, but for this, I would say aim low, not aim high. So people will say, oh, I'm just going to model all of this stuff. So I'm like, that sounds more difficult than a thesis project, and you've essentially only 3 weeks to do this as one of your 6 modules. It's not a thesis project over the whole year. So aim for just some particular component or part of your thesis project that you want to model. And don't go too crazy. It's fine to be 2D or something. Even maybe check it works with 2D, like 3D model or something like that. Yeah. Are there any other questions on that? Yeah. So for every answer, for every question in the quizzes, there's feedback that I've typed in. So if you get it right, there's like feedback. If you get it wrong, there's feedback. So when you do it once, and for every wrong answer you select, and also I should let you know that there are multiple answer questions, which also makes the brute force approach more inefficient. So if there's 5 answers, the correct answer could be 5 of them or 1 of them. It has to be at least 1 of them, but often it's just 2 or 3. So if you take 2 correct and then 1 wrong, then I think it shows the feedback for the 2 correct and the feedback for the 1 wrong, if that makes sense. So if you just go in and tick everything the first time you do it, it'll give you all the feedback for everything. I guess that's probably one approach, but it's not that helpful because it doesn't tell you. No, don't worry. I've thought about that. So it doesn't help. It doesn't tell you which feedback is which answer. So it just gives you a load of text in some order. Each sentence is feedback. So it'll say, well, like an adiabatic condition is the same as the normal gradient of temperature being 0 or something like that. So some of them might be clear, but some of them won't be. So, okay, you can do that anyway and just see you get all the feedback. And I don't mind as long as you learn whatever you're going to look at. So it will tell you which questions are wrong. So it'll give, if there's 10 questions, it will tell you how many points out of 1 you get for each of them. And I think you can get fraction marks. So say if there's 3 right answers and you get, say, 2 right and then 1 wrong, I think they cancel out. So you get 1/3 of a mark for that one. Or if you get 2 right and you don't set that down, so you get 2/3 of a mark or something. So you'll see how many marks you got in each one. So you'll know which questions you got wrong, and then you get feedback on in right or wrong answers. So you won't definitely be sure, but you probably can figure out which ones you get. And that answer. Do you have a follow-on question? It's also a good question. So the way I've set it up, I can set it up to any of those things, but I've set it to be the final attempt. So rather than, once again, maybe I'm putting too much weight on people doing brute force approaches, but rather than just people blasting out 10 guesses of quizzes and then just taking like the best of all of them, that doesn't make sense to me. So it's just your last one. So that it has happened in previous years where people, they got up to 9 and then they tried it again and they forgot what the previous answers were and went down to 6 and sent me an email saying, can I just go back to use the original one? So no was my answer. So it defeats the purpose. Like the purpose is for you to learn it. So not for you to randomly get it right. Yeah. Any other following questions? No? Other questions?
Is each quiz just on the different softwares?
And it's on the content. It's not limited to the particular software. It's broadly related to. So in Abacus uses the finite element method. So it'll have questions about the finite element method, the background to how to set the problem. So it's broadly related to what we got in the first 3 weeks of lectures and the labs, and then the same for second and third, but it's not fully limited to it. So the questions, you'll see when you click into it, like you click into the quiz and see the questions, and you don't have to submit anything, and that doesn't cost you any attempts. So you can always just click in and see the questions and then have a look. You can go off and study the answers if you want to then, and then go back. So if you just click in to see, you'll see these sort of questions, but there's not that many questions which are, let's say, super software specific. It's not like I put a picture of a button and I'm like, what does this button do, or something like that. It's more to do with the theory of, if you set a boundary condition like this, what is the behavior you should expect, or something like that. So once again, the emphasis is kind of to be software agnostic, that I want you to learn the method so you could use any software. It just happens that we have abacus and answers. Other questions? Okay, so in terms of these lectures and the labs, for the lectures, will broadcast it using Zoom. I think I did that this morning for another lecture, and it seems to work okay. I listened back and the sound is actually okay. And I think I'm relatively close to my laptop and I have a relatively loud voice, so it's actually okay. So you're welcome. You can attend from online if that suits. I know some people were worried that they live far away and Friday afternoon is not people's favorite time to come to lectures either. So that's fine as well. The labs, we could do that if people want, just to get help from the labs. I can ask the teaching assistants to set up a Zoom session, and you can just log into Zoom, just work away. And if you have questions, then you just ask questions via the Zoom session, or like apply to breakout room. So last year we did it all online. So I would just make a breakout room for every student. And if they had a question, they go in and click the request help. Then I just go in, they share the screen, and I just help them with your software as if I'm kind of side. So we can do that as well if people want that. Maybe just put a comment in the discussion forum or just send me an email. I'm going to assume you don't want it unless you tell me, because it's just more effort for us. Less nobody if nobody wants it. I'm to help with the quizzes. You'll see I put up a lot of content online that I'm not going to get through in the lectures. So I'm picking out the important ones to go through in lectures. So the rest of the content is to help you answer the quizzes, and I will make some short recordings, not full long lecture recordings, which are tough to go through, but maybe like a 10-minute, I don't know, finite element method in 1D or something, and I explain some of the methods, and I make these like a little short video recordings. So I'll put those up, and maybe I'll put a comment saying this will help answer quiz 1 or something like that. And that is it pretty much. So yeah, it's probably not a good time now, 3 minutes to go to start on another set of slides, right? So I'll just leave there. So thanks very much. And if you have any questions, you can just come ask me afterwards or wherever. Thanks.